A couple reminders about properties that functions can have. So we say that a function is onto, so a function with domain D and range R, we say that it's onto when every element of R, the range, is taken on as a value of the function. So in other words, for every element of the range, there is something in the domain that the function sends to that thing in the range, right? So if you sort of pictorially, if you have a domain with, right, all of these elements in it and a range with some elements in it, right, you can draw a function as arrows that tell you where in the domain goes to where in the range, right? So move my R over here. And a function is onto if everything, so I need to draw an arrow for this one, a function is onto if everything in the range gets hit, right? A function is not onto, so here's domain, here's range. A function is not onto if there's something in the range that does not get hit by something coming from the domain, like that. So this is not onto. So some examples, I mean, the function going from R to R given by this formula, f of x equals x, this is onto, right? Because is it the case that every real number is an output of this function? Well, yeah, every real number is an output, because if I give you a y in the real numbers and you want to find an x that you can put in here to make y come out, well, you can just put y in and y will come out, right? So every y is an output of this function. So this is onto. Okay, now contrast this with the function g going from real numbers to real numbers, given by this formula, g of x is x squared. This is not onto, because is there a real x so that g of x is -1? Is -1 an output for this function? No. There's no real input that will produce -1 as an output for this function. So this function is not onto. But notice that actually if we slightly modify this function, so I'm going to call this modification g hat, if we slightly modify this function so that its domain is real numbers and its range is numbers from 0 to infinity, not including infinity, this is onto, right? Because by throwing away the negative numbers in the range, now when we ask the question for every value in the range, is it produced as an output? Well, we've thrown away the ones that aren't produced as outputs, so everything that's left is produced as an output. So this function is onto, so g hat is onto, but g is not onto, right? So the property of being onto actually can depend on what exactly your range is, right? So got to be a little careful with onto. But right, if you keep this picture in mind, you'll keep it straight. Onto just means everything in the range gets hit by something. All right, well, onto is one side of a two-sided coin, and the other side of that coin is being one-to-one. So a function is one-to-one if different inputs get sent to different outputs. So a fancy way of saying that is for two values, x1, x2, in the domain, if those values are not equal to each other, then f of those are not equal to each other. An equivalent way of saying this is if you have two inputs that produce the same output, then those two inputs actually were equal. So this pictorial way of drawing functions, if we, so the way, what one-to-one means in this context is, so different inputs are just different dots here. And so to have different outputs, well, they have to go to different dots, right? So this would be one-to-one. So I can write one-to-one just like this, one-to-one. So this is one-to-one. But if we wanted to see what it would look like for a function to not be one-to-one, well, we would have to have two different outputs going to the same input. Sorry, that's backwards. Two different inputs going to the same output. So if it were like, say, this is not one-to-one Because right here we have two distinct inputs that go to the same output, right? Which violates this statement here. So that means this function is not one-to-one. The way that I've drawn it, it might appear that if a function is not one-to-one, then it can't be onto because we've missed a value here. But that actually isn't the case, right? If I just delete this, if I modify the function slightly so it's like this function is onto, but it isn't one-to-one. So being onto and one-to-one, they aren't necessarily related to each other. So some examples of being one-to-one. So we can actually look at the same two functions as we did when we were thinking about onto. So for f of x equals x, you can see that if x1 is not equal to x2, we can ask, is f of x1 equal to f of x2? Well, no, because f of x1 is x1 and f of x2 is x2, and we already said that these were not equal, so these aren't equal to each other, right? So if we have distinct inputs, the function f produces distinct outputs, and so that means that f is one-to-one, right? Contrast this with g, which is the squaring function, right? So are there distinct inputs that produce the same output? Well, right, this is a universal statement, this property of being one-to-one. So to show that g is not one-to-one, we only have to produce a single counterexample, and it's not hard to see what the counterexample is. Can you think of two different inputs that produce the same output when you square them? Well, sure. How about -1 and 1, right? So here is an example. So g of -1 is equal to g of 1, but of course, -1 is not equal to 1. So here are distinct inputs that give the same output. So that means g is not one-to-one. All right. Now, the nicest kind of functions are both one-to-one and onto. And functions that are one-to-one and onto are called one-to-one correspondences, or sometimes just a correspondence. Although, in my experience, one-to-one correspondence is slightly more common terminology, but either is fine. And the reason why one-to-one correspondences are so important is because any function that is a one-to-one correspondence, or I should say a function is a one-to-one correspondence if and only if it has an inverse function, right? So this isn't hard to see. I won't prove it in detail, but this isn't hard to see why this has to be true. If you have a function that's one-to-one, right, that means all of these arrows, none of these arrows can go to the same place. But if it's also onto, that means they hit everything in the range. Well, then you can define the inverse just by turning all the arrows around, right? Because your function was one-to-one, the sort of reverse arrows, the red arrows going from right to left, none of them start at the same place, since none of the original arrows ended at the same place because of one-to-one. And since none of the arrows start at the same place, since no two red arrows start at the same place, this actually does define a function. And since the original function was onto, we actually have an arrow to turn around at every point in the range. So we can define the inverse this way. So if a function is one-to-one and onto, you can write down its inverse explicitly. On the other hand, if you have an inverse, then it's pretty straightforward to prove that the original function was one-to-one and onto, because if it's not one-to-one, the inverse can't be a function. And if the original wasn't onto, then the inverse can't even be defined because there's some point in the range that doesn't have an arrow coming from it for the inverse. So being a one-to-one correspondence is exactly what you need to have an inverse function. So, for example, is this function from the real numbers to 0 to infinity given by this formula a one-to-one correspondence? Well, no, because it's not one-to-one, right? We've seen that already. Now you might think, well, wait a second, doesn't this have an inverse function, the square root function? But the square root function isn't quite an inverse function, right? An inverse function has to satisfy this, right? for an inverse function, if you do the inverse and then the original, you end up where you started, right? You're going around one of these closed loops here. And also, if you do the original function and then the inverse, you also end up where you started. That's going around a closed loop, but sort of starting on the opposite side. But the square root doesn't always undo the square function, right? Because if you take the square function and put it inside the square root, do you always get back where you started? No, because if x is negative, you don't get back where you started. You get back to the absolute value of where you started, right? So this isn't one-to-one, and we see that reflected in the fact that it doesn't have an inverse. Now, it almost has an inverse. We can sort of fix things up by modifying this function, right? If we modified our function f to come up with a new function f hat, and we throw away some of the domain and only keep the positive numbers in the domain, right? And f hat of x is x squared. Now this is one-to-one and onto. Right? It's clearly onto because every positive number is the square of something. And now it's one-to-one because we've thrown away all of the negative values, which is what was ruining our one-to-one-ness earlier. And we can even write down the inverse, right? The inverse for this function is just the square root function. Because we've thrown away the negative inputs, this problem never happens. So this just goes to show that when you're thinking about whether a function is one-to-one and onto, you can't ignore what the domain and the range are. We kind of have a tendency, especially in pre-calculus and calculus situations, of thinking about functions just as the formula that defines them. But that's not really what a function is, right? A function is a range, a domain, and some rule that turns domain values into range values. So you can't really ignore what the domain and range are. And we're seeing that reflected in the fact that these properties of being one-to-one and onto can change if you change the domain and the range. Right? That's just a reflection of the fact that the domain and the range are critical parts of defining what a function is.